holiday prep.
And just a disclaimer, the 4th of July, we're not really talking about like the history of it, we're talking about the modern day like activities that people tend to do over the holiday. So, they got a calendar. So, a little bit of history behind the 4th of July. It's called the 4th of July because it occurs on July 4th. And the first day was 1776, and that is the day that the final wording of the Declaration of Independence was officially approved, but it wasn't actually declared a national holiday until 1870. And now in modern day times, it's a really popular holiday for big fireworks shows, potlucks with lemonade and stuff, and trips up to the cabin and boat rides and stuff.
Going up north.
So why we chose it is because it was all of our favorite holidays. It's a broad topic, and it was easy to find calculus-related topics. Also, who doesn't love lemonade, sparklers, swings, kayaks, and popsicles? I don't think we would find many people who don't. If you do, that's shout out to Mark Porter.
Yeah, most patriotic dog around. Give him a follow. Okay.
So for part one, we have a video of Rachel swinging. We wanted to use a rope swing, but the water was really high, so when she did it, she actually hit the water, so that kind of screwed up our graph a little bit. So we decided to use just a swing. Question?
Yeah.
Is that Lake Alexander?
Yes. Yeah, so I tried to do a rope swing, but it didn't work out.
Today they're just swinging, have a grand old time.
Yep.
Okay. Such grace.
Okay, so after that we used capstone. I learned how to use it in physics class. And so I was able to graph each point of when she was swinging, and as you can see, it makes a parabola that is concave up. So this is the position function, and it actually gave us the equation of it, as you can see right there. And then we also have the velocity. As you can see, it kind of goes up and down, which is a little unusual, but that gave us the line of best fit, which we used. And this is also the acceleration. We have the equations for those as well.
So like for this one specifically, you can tell that it's negative because you're going to be going like backwards some and then forwards.
Yeah, let's
So
just
that's
showing the direction.
showing the direction. That's why it gets positive and then it's negative and then it's positive.
And then you can see that at that point where it changes from negative to positive, that was where she hit her minimum point of the swing.
Okay, so then we decided we wanted to figure out some speeds of how fast I was going during my swing. So, yeah, and then we also are going to find the average speed later to compare them to all the speeds that we found. So we just picked different points where I was swinging, and we plugged those points into the velocity function. So the first point was 0.5 seconds, and we actually got negative 0.3755. And that would be the velocity, and the negative just shows which direction you're going in. So the speed would actually be a positive 0.3755, and then we just plugged in some more points at t equals 1. The velocity is negative as well, but the speed would be a positive 0.073 meters per second. And then at t equals 1.5, we just get a positive 0.2 meters per second. And at t equals 2, we get the highest speed, which is 0.5 meters per second. So that was pretty fast.
And the time it took her to get from one side to the other was actually, I think, 2.31 seconds. And the total length was like 130 centimeters or something like that.
Okay, so then we decided we wanted to find the average speed and velocity, and this is probably our most challenging problem. We had a few issues with this one, but so first we knew that we needed to do the integral of the equation and then over b minus a, and we knew that would give us the average velocity, which is negative 0.073 meters per second. And we kind of were thinking that we could do the same thing with the speed and just like get rid of the negative, and that would be the speed. But we realized that the average velocity was accounting for all the negative velocities and the positive velocities, and all the speed is positive. So we knew that we had to have an absolute value sign in there in order to get the average speed. So then we did the same thing. We took the integral from a to b of the equation over b minus a, and then we got the average speed is 0.3 meters per second, which makes sense with all the points that we found. It's about right in the middle.
Alright, so the next part we did is lemonade. So Mr. Kruger helped us model a function, kind of the rate at which lemonade would be consumed at a potluck. So the potluck lasts 3.5 hours, and it's measured in cups per hour. So this is the function that we got from the velocity. So as you can see, like at the half an hour when lots of people are going to be there, the rate at which people are going to be drinking lemonade is going to be really high, and then it's going to go down for a while and back up. So kind of like as the day's going, the rate at which people are going to be drinking lemonade. That's what this models. And so then we way, we wanted to find the antiderivative of that, so that's going to be the area underneath the curve, because that would model how many cups of lemonade we're drinking that time. So since it isn't strictly increasing or decreasing, we couldn't tell if the left Raymond sum or right Raymond sum would give us the overestimate or the underestimate. So like in the left Raymond sum, this is what it is, and there's this area that's unaccounted for, but then this is over. So we thought it would even out. So this is the left, this is the right. So here's all of our calculations. We did 7 subintervals that were half an hour long each. And with the left Raymond sum, we found that 19.141 cups were consumed. And then with the right Raymond sum, we found 17.5 cups. So looking at that number, it's easy to tell that the right Raymond sum ended up being the under approximation, and the left Raymond sum ended up being an over approximation. So then, to be able to find the exact number, we integrated the function that we got modeled on GeoGebra from Mr. Kruger, and we modeled it from A to B, which was from time 0 to time 3.5 of the function. And then we found that exactly 18.904 cups were consumed by the party at the potluck. And if you go back a slide, you can see that it was right in the middle of the left and the right Raymond sum. No, it was really close. Well, it wasn't in the middle, but it was between them. That's what I meant. But then it was really close to the left Raymond sum.
Yeah, it was only off by about 0.3 decimal places, so in that case, left Raymond sum worked out.
Yeah, the left Raymond sum was much more accurate. So then after that, after we knew how much lemonade we went through, we wanted to take the derivative of the velocity function, and the derivative would give us the acceleration. You might be wondering why the acceleration is important when we're talking about lemonade, but it's related to like if you're at a restaurant and the acceleration of people coming was really high, you'd be in a rush, there'd be lots of people coming at a specific time. So like here you can see when it's above the x-axis, that's where it's going to be positive, so there's going to be a lot of people coming at once. But when it's below, that's when the acceleration is going to be negative, so there's going to be less people coming.
And you also want to know how much you need to be refilling the lemonade so that you don't run out.
So like we found that we went through 18 cups of lemonade. So if you had like a certain number of cups filled, you would know how often you have to refill cups without running out and people not getting any. So some of the math involved is we looked at it and we saw where the acceleration is positive, which is on these three intervals, from 0.356, 1.456 to 2.54, just these intervals. And then it's negative on these, so we know that on this, there's going to be more people coming at a rate faster, and then this one, the rate's going to be going down. So we need to worry less about refilling lemonade.
Okay, so the third part of our project is about the annual kayak trip. So at my cabin, my dad and I, each year we kind of just go on a big kayak trip around the islands around my cabin. So in this problem, it's my dad and I kayaking, and I'm heading home from Haystack Island back to my cabin. And my dad is coming to Haystack Island from Greens Island, and I'll show you a model of that on the next slide. So the goal for this one is to find the distance between my dad and myself at various points, and this is the rate at which we are paddling. I'm going 220 feet per minute, and my dad is going 264 feet per minute. So this is just showing our pathway. This big island is Greens Island, and my dad is traveling 264 feet per minute towards Haystack Island, and I am coming back from Haystack Island to my cabin, which is directly below it, and I'm traveling at 220 feet per minute.
So the distance we're finding is from, like, if her dad is here and she's, like, here, it'd be whatever distance this would be. So the hypotenuse of a right triangle.
And we got this image using Google Earth.
So to start this off, we just wanted to find the distance between the 2 points. Right away, we use the Pythagorean theorem. So when I'm 150 feet from Haystack and my dad's 100 feet from Haystack, we could find out, using the Pythagorean theorem, we knew that the distance between us was 180.278 feet. So using those numbers that we just found out, we knew we wanted to do a related rates problem. So the goal of this is to find the rate at which the distance between us is changing when I'm 150 feet from Haystack and my dad is 100 feet from Haystack. So like when we're doing a related rates problem, like always, I listed all the variables on this side. These are where we are from Haystack, this is what we just found, and these are the rates that we were paddling. So we know that we need to find dc dt, or the rate at which c is changing. So over here, we started out with the Pythagorean theorem, and we took the derivative of all of it. And so we wanted to get dc dt by itself, so we divided by 2c, so that 2c was being divided over here. And since we have all these variables already, we could just plug that all into the equation and pretty easily calculate that the rate at which c was changing is 329.491 feet per minute.
So the next part, we wanted to find the volume of a popsicle using integration, also known as the disc and washer method. So what I first did is I traced and graphed the popsicle. It was pretty hard because the popsicle kept like dripping on the paper, and it was kind of hard. You had to do it pretty fast, otherwise it would melt.
We also could not find graph paper.
Yeah, it took us a while to find graph paper and a ruler. You would think that'd be like around your house somewhere, but it
It's
took us a
amazing when
long
you're not
time to
in
find
elementary
a
school.
ruler.
It's amazing when you're not in elementary school, you'd never use a ruler anymore.
So then I measured it, I put it on a graph. As you can see, it's scaled. The popsicle was 3 centimeters long, so you can see that it's only 1.5 meters tall. That's the x-axis that crosses in between it. From 0 to 9.5, that's the rectangular part of it. And then as you can see, it makes almost like a half circle shape, and that's only 1.5 meters long. Centimeters long. So what we did next is we found the equations, as you can see. So we have the x equals 0, we have y equals 0, and then we also had x equals 9.5, which cut it in between the rectangle and the half circle, as well as this right here, which is the equation of that. And then, so we decided to integrate, which would be rotating around the x-axis using the disc and washer method. So we plug those numbers in right there. From 0 to 9.5 we integrated, and we found that the volume of the rectangular part was 21.375 times pi centimeters cubed. And then also over there we found that the volume of the half circle was about 1.125 pi centimeters cubed. So the next thing we did is we had to add the two solutions together to see what the total volume of the popsicle would be. So adding those two together, it was about 70.686 centimeters cubed. And so I wasn't really confident in my answer. I wasn't really sure if that was right or not. So to check it, we found the volume using a rectangular prism and a hemisphere. And adding those two together, we got about 71.194 centimeters cubed, which is pretty close and rough estimate of the popsicle.
And then one frustration we had with this was I wanted to find volume using another way. So the rectangular part, so not the half circle at the top, but the rectangular part down the bottom. I wanted to find that using rectangular cross sections because this part of the popsicle down here isn't a perfect cylinder. So rotating around the axis would give you a cylinder. But I wanted to find it using rectangles, so it'd be more prism-like. And when I did that, we found it to be about 90 centimeters cubed, which we thought was really way off from the two other ways that we found. So then we looked at it again and we found that this was more rounded than we originally thought. So
also another idea we had was to see how many popsicles that could fit into a normal size freezer, like the one on top of a fridge. And that was kind of hard because you had to take an account of the popsicle stick. So the stick was about 1 centimeter cubed in volume, but that didn't take into account the packaging around it. And when we figured it out, we got a really large number, but that was just an idea we had that didn't really work.
that didn't really work. Pan out. Alright, so now here's where we get to more of our frustrations. We tried to do a lot of different calculus because since this thing is so broad. We thought we wanted to do something with sparklers because if you leave the exposure open for a long time on a camera, you can take pictures with writing things out with the camera. I'm not with the camera, with the sparkler. So like here's Bailey, she's writing an integral sign with a flashlight on her phone.
Yeah, that wasn't even a sparkler. That was just me like turning the flashlight on my phone, and I just like waved it around in this motion, and then she like it wasn't open as long as 15 seconds. I think it was only like 6 seconds.
It was like 2. It was on my phone, and the exposure was open for like half a second, and we got that picture. So I found some really difficult calculus online where you could figure out like the volume of light that goes into your camera based on how long the exposure is and the aperture setting, because that's how fast it opens and shuts. And the problem we ran into is because it's open for 15 seconds and it opens so fast and shuts so fast, you can't really calculate how fast it opens and shuts. So we weren't able to find like the volume of light that went in. And this picture is because we were trying to figure out how to take a picture without flipping it. So we were trying to like write words.
Yeah, so I was like trying to see if we could figure out a solution to not having to write backwards so that you could see it front facing on the camera. Because with the sparkler we had to write everything backwards so that we were able to read it. So we were trying to test out if we could just use the front camera and see if it would flip it for us, but as you can see, it didn't really.
Yeah, and I also used a sheet that had like our function on it for the lemonade. So yeah. So here's us trying to write we wrote calculus with a sparkler.
Yeah.
It took shout out to Jaden for
Letting
working.
us-
Yeah, he was the one that lit our sparklers and he brought us ice cream because we were getting really frustrated with this. But so we went to Bailey, Rachel's house, and we had the aperture open for 15 seconds. So I would stand in there holding a camera for 15 seconds while Bailey would.
Yeah, it was kind of difficult because we had to find a spot where the light wasn't too bright so that it wouldn't cause problems with the picture. So we had to go. There was just like a random house.
We're like in
there.
the street right now.
Yeah, we're in the street, and so I'm like writing it backwards. I actually started this way and wrote it that way, and they had to keep telling me to like make it super duper big, otherwise
Rachel's
you
our
wouldn't be
hype
able
man.
to see it.
Rachel was our right man.
We couldn't really find a lot of calculus like in the sparklers. We just thought it was really cool.
Yeah. we saw
Yeah,
that.
and then we also thought maybe we'll want to do something about like how the rate at which the heat changes. But then we'd have to have like a temperature sensor. But then the sparkler was so hot that it burned the temperature sensor. So we had lots of ideas of how to apply calculus to sparklers, but then none of them panned out because they were all so difficult to use. There's Mr. Kruger.
Yeah, we tried to do that. We actually had Rachel was like on the bottom and I was on top. So
And that's just
I
my
did
flashlight
the top.
on.
I did like the top of your head, and she did the bottom.
I did
so
the beard,
did
but it
top.
kinda
So she had to do the glasses and then she did the beard, but then they kind of like got off track over
Yeah.
there.
But it was an intense.
It was intense. So yeah.
Okay. That's
Mama June.